for today, and hopefully at 30. Okay. And now I put on the so in this class, there are really four related topics, as you can see here. So I'll stop at the end of each one and see if everybody's caught up. First we say, what are reaction diffusion systems? They're a particular case of dynamical systems where you have, effectively, we gave this as, without that, as the definition of a reaction diffusion, of a dynamical system before, right? As if U1, U2, etc. were scalars. And we wrote it as a vector, d by dt of U vector equals F vector of U vector, right? And that's still the definition of a dynamical system. But now we are assuming that U, all these U variables depend, we did that implicitly before, but now we're doing it explicitly, depend on spatial variables, X. So there isn't really just one U1, one U2, one U3, there's U1 at all the places in space, U2 at all the places in space, and so on. So it's not if there are n species, it's not an n-dimensional system, it's an n times the number of spatial points. And hence, you see that this diffusion, which takes into account a single U, but with different spatial coordinates, fits into the reaction diffusion framework. So all we've done here is separate the two dependencies. That is to say, this term, for every x value, it's evaluated at that same x value. You can say it's diagonal in space. Okay, it's local in space. Okay, every x value concerns this x value. But it concerns the different species. We'll talk about it for the moment as though it's chemical species. The notes are already there?
Yes.
Oh, good. Thank you so much. So that's the reaction part. The diffusion part is the opposite. That is to say, we're not talking about cross-diffusion. We're talking about the diffusion of a single species one at a time. And so this term here, for the ith chemical species, concerns only the ith chemical species, but at different places. So this is coupling the different species, and this is coupling the different spatial locations. Okay, everybody? It's just, it's still a dynamical system, but it's just a particular kind of dynamical system, and we've decomposed the right-hand side into two pieces, which are diagonal in the spatial versus the species variation parts. Okay. So one of the main ways that dynamical systems theory is used in chemistry is to describe the oscillating chemical reactions, such as the famous Belousov-Jabotinsky reaction, which was discovered in the 50s and 60s and was very popular in the 70s and 80s, but also in other phenomena, biology and social sciences, and even physics and engineering. Let me see if I can let me get out of this for a second. Let me see if I can get. It's Pi Day. Happy Pi Day.
Oh, really?
Or is it? Is today the 14th? Yes. Okay.
Yeah, 314. Okay.
In American ordering. Here in Australia, you do 14-3, right? The sensible way. We're going monotonically first. There should be a film here somewhere. This one seems pretty short. Let's do this. So this is a chemical reaction here. You see it's forming spirals when it's fully developed that annihilate with fronts of the opposite sign. And let's see, this one's so, here, there's lots of them. Oh no, so rock, paper, scissors, those, no, that's not what I want, I don't think. No, let me not do this one. Go back. Oh, it might be, go back again. Let's do this one. It's not too long. Yeah, this looks more like a chemical reaction. You see the Petri dish here. And what's going to happen? Come on. There, you see the target patterns. You see it start to form there. Later, let's see what these sparks. The contrast isn't quite as good in colors. But I guess maybe it makes you feel it's realistic. Is it going to oscillate? Come on, let's go. Let's oscillate. It's supposed to oscillate. Come on. It's oscillating awfully slowly. It's got bubbles. Oh. Wasn't it oscillating? I don't know. It says oscillating, doesn't it? No. Well, let's go back to find another one. Too much talking. Okay, and now stirred up. Okay, and there. Okay, so it oscillates. It turns from blue to red. And you see they had to stir it. Why is there a stir? It's to keep it from forming patterns. Otherwise it forms patterns. But just stir it, it's going to go from blue to red. Now you see it formed a pattern. Again, stirred up. And it's going to be blue. And you leave it, and it's going to be red. And now it's going to be... Oh no, it's forming a pattern because it didn't stir it. Okay. Music. Okay, so we go back to the class. That's the Belousov-Jabotinsky reaction that's mentioned there in that, and I think that perhaps started this the formalization of reaction to study of reaction diffusion systems, but I'm not sure. Okay. Yes.
The point you mentioned that in the diffusion term, it's for all that particular species present in all spatial locations.
Yes.
But mathematically, if we see like ui has to be a function of all the spatial variables. So if we say del ui by del t, so
yes.
The right hand side, if it's a function of ui, it has to be at that particular spatial location, right?
The reaction, yes, the reaction takes place locally.
Term.
The diffusion term, no. The diffusion term, it's the opposite. What diffusion is if you have a lot of U here and less U here, then you tend to give some of your U to your neighbors. It doesn't concern the V, say, either U1, U2. You diffuse your own species outwards, and if you see a big bump in U over there, it flattens out and gives some of itself to you. It doesn't concern the different, it's not cross-species.
No, I wanted to ask, like, it's for the same species, but it will depend on the property of that species at that particular location, right? What is the concentration gradient at that particular location?
Well, I should say, this thing is supposed to be, this diffusion constant is supposed to be for that species. I would say that the gradient and all is already taken into account here. You know of Fourier's law, some that's what maybe Fick's law, you know,
Yeah,
how
Fick's
they
law,
made
I was talking
diffusion.
with
That's
respect
right.
to that.
But this thing here is the Laplacian. So that is how to take that into account. The gradient is in there. Right? Is that right? Or am I understanding what you're asking? Yes, it depends on the gradient. It depends on the variation. That's what the Laplacian is doing there.
Yeah, but you told like if there is the same species at some other spatial location, this term accounts for the effect of that species as well. I mean, the same species UI,
Yes.
but at different spatial location is also accounted in this term.
And very weakly, yes.
Okay.
I mean, the Laplacian is a global operator. If you have a function and it changes over here, that's well, point-wise maybe not. Yes, no, I think so, because if you take a Fourier transform of a local function, it has components in all frequency, in all wave numbers, and so yes, I believe that you will then be affecting the wave numbers, and hence will also have an effect here. I think it is not a local operator. The Laplacian is a global operator. Naturally, it has the most effect. Mostly, it measures the curvature at your exact point. In fact, that is what it measures. But if you change the value someplace, that will affect the curvature where you are. Is that really true? I guess that's only true if you change it in an analytic way, and changing by a point would not change it. Okay. I think maybe if you really just changed a value here, it wouldn't change. But if you put on a perturbation that was mostly concentrated there, but not a point particle that was analytic, so it was a bump, if you put on a perturbation like that, that would be felt here. I think that's true.
So another way to see is that suppose I was computing this numerically, then at a particular location, I would, in this diffusion term, I would have to take contributions from all the grid
Yes,
points.
that's right. That's right. Not equal contributions.
Yeah,
and of
I mean,
course,
that would depend.
that's right. And of course, if you do a finite difference method, indeed, that's the order, the spatial order of the method. The more points you take into account, you can take into account just your nearest neighbors, and that's a first order method, and you can take into account the next ones, and that's a second order method, and usually you stop there. But if you do a spectral numerical method, then you're taking into account the points arbitrarily far. But mathematically, I'll repeat this point, that the Laplacian is a non-local operator, and when you solve a Laplacian f equals g, as one often does in physics, that depends, every point in g is affecting the solution at every point in f to some extent. Okay, so here are the simplest thing is to have two species. Here are two model reaction diffusion equations, or rather the diffusion part stays the same, but we will just look at the different reactions. And so everything reduces to 2. We have f of u and v, g of u and v. The spatially homogeneous version should be studied first. Let's simplify and just do a two-dimensional dynamical system with two variables, u and v. And here are two models, one called Fitzhugh-Nagumo model, and the other called the Berkeley model. And this, so you can see, it's away from the abstraction of that we have presented here, back to something concrete that everybody can understand. Here we have f is a cubic function of u, and here also f is a cubic function. And g is a linear function. You see you have terms that contain u and v. And u and v. Okay, so what I'm introducing here now, not something that's so sophisticated, but a way, as I said before, dynamical systems is not a particular object, it is a particular set of methods. And so too now reaction diffusion systems brings their own set of methods. There's nothing so difficult about these equations, but let us study them from the point of view that's usually used for reaction diffusion equations, and that is with isoclines. This is the space u and v, both of them are the space u and v, and what is being mapped here are the null clines. This is the red is the set of values for which f is 0, so you see v has a cubic relationship to u, you can see it's a cubic, right? V, that's the set, we've substituted 0 here. We're looking for fixed points of the spatially homogeneous system. G is the null-cline of V, so it's the set of points for which this expression, this linear expression is 0, and that's a straight line. Okay. And a fixed point is a point at which both f and g are 0. Neither u nor v change, and so that's the intersection of those two null climbs. Okay, that point. This Berkeley model is also cubic, but because it factorizes so well without v appearing in either of these, what you end up with is, for the null climb, there's one section that's u equals 0, one section that's u equal 1, and one section that's u is a linear function of v. Okay, and this is the so it's a kind of degenerate cubic. This is the red is really the zeros of is a cubic, but a very special looking one because of its factorization. And the g is the same, or not the same, but also a line. And again, there's a fixed point where the red, the f equals 0 curve intersects the blue curve, the g equals 0 curve. And from what we've learned already from the very first time, this, again, we're only doing the spatially homogeneous system now. So we have all the ingredients that we need, that we've done before. We take the Jacobian, we have the fixed points, remember the sequence of steps to find the fixed points, find their stability. We take the partial derivatives of f with respect to u and v, and of g with respect to u and v, and that gives you the Jacobian. And this fixed point is stable if the both eigenvalues of the Jacobian have negative real part. Okay, all this was introduced in the very first class. Okay. Now, what is excitability? For this now, we're going to look at the null climbs, and we're going to do, as we did in the first class, see what those curves of f and g mean. Remember, f is the direction in which u evolves. So positive f corresponds to arrows going to the right, negative f corresponds to arrows going to the left. Similarly, g describes the direction in which v evolves. So a positive g corresponds to arrows going in the upward v direction, and negative g corresponds to arrows going in the downwards direction. So we're going to do that with this system here. Of course, when you hit a red line here, that's when f is 0, and hence you change from a rightward to leftward motion of u. Right? It's to change between positive and negative. And you can see that for u sufficiently large, you have a negative sign, and hence it's leftward motion. And the rest all follows. You have to change signs when you get to a red one, and then you have to change signs when you get to a red one, and then you can verify. I mean, by now you know everything, you only need that little bit of information, but let's verify for u sufficiently negative, u times minus u times u is also negative, and, is positive. U times minus u times u is, for u negative, that's positive, and that corresponds with that arrow as it should. Okay, so that explains these arrows, these horizontal arrows. The vertical arrows, well, again, we had the null climb that was blue here, and we changed signs, and all we need to know is one direction of one arrow, and then everything else is figured out. Well, for v sufficiently big, then g is negative, right? So arrows way up here, I mean, they can only change sign here. The arrows in high V are downwards, g negative, and so you have downwards arrows. They have to change sign when they hit this blue line, and so they do that there. Okay, so these are the elements for what we need. Now we're going to put them together here. We're going to add up those green vectors, they're vectors, and note that here there is an epsilon, and so f is bigger than g, 1 over epsilon, and hence these horizontal arrows have been drawn bigger than the vertical arrows. Okay? So let's put these together. Over here, since there is no horizontal motion, let's see, what is it? No, excuse me. There's no, okay, some of it is easy. On this, there is no vertical motion because it's a, do I have this right? Yeah, no, wrong, sorry. There is no horizontal motion here, because it's where F is 0. There's only vertical motion, and we see over here from these arrows, this is on this side of the blue curve, that it's downwards. So we have downwards motion along this red, this milk line. By a similar argument over here, we have only vertical motion. There's no horizontal motion because it's 0 here, and that arrow that corresponds to that region below the blue is upwards. So these arrows we already have. If we add together a little bit of rightwards and a little bit of upwards, we get, a lot of rightwards and a little bit of upwards because of the 1 over epsilon, we get an arrow that's like this, a lot of right and a little bit of up. In this section, we have to add some left and some up. That's what this is in this region. In this region here, we add some down and some left. We're in this region of the red null lines. Some left, a lot of left, and a little bit of down. That's this. And here, we have a little bit of up. And we're not far from the red null line, so we also have just a little bit of left. Okay? So this is the circuit that you see. And we give these names. This is called the U equal 1 is called the excited phase. U equals 0 is divided into 2 pieces here. One of them is high here, and over here for high V, we call that the refractory phase. And for low V, we call that the excitable phase. And this line here is the excitation threshold. So what does all that mean? If we're here and we get a little perturbation to the right, well, we come back. If we're here, we get a little perturbation to the right, and then we come back. If we're here, we get a little perturbation to the right, and we come back. But by the time we get here, it doesn't take much of a perturbation to bring us across the blue line. And we see that we are in a region now where we go rightwards. And when we go rightwards, we go all the way here, and we come back. Yes, this is a stable fixed point. And the only stable fixed point of the system. And we will come back to here, but we will come back by doing all of this. And that, as opposed to if we were here, where we got a kick, we would just come back straight away. We would need a very big kick to go all the way around. Okay, this is the size of the kick that is needed to get you away from this region. And now let me see if I can get a picture of that. I think I can. Let's see.